what I tried to do on these is, again, in your notes, I think there was like 108 integral formulas. I was joking at you and telling you have to memorize them all. You don't have to memorize them all. You're going to look them up as you need to. So let's see. Let's look at this one. We've actually learned how to do this one without looking up an integral table before. So this one, the way we learned how to do this in the past was, that looks like a completing the square thing, right? Okay, so we're going to do a completing the square before we go to the integral table. I went ahead and just showed you number 14 in your integral table would be what you'd be looking for on this one, and you have to put it in a factored form to write it in this x squared plus a squared form then. Okay, so what we're going to do first of all is we're going to complete the square. So you want to go ahead and do that. Okay, and this one's kind of set up kind of nicely. So again, remember what you do is you take half of the 2. So if you take, divide that by 2, you get 1. Then if you square the 1, you get a 1. So we're going to do a plus 1 there and a minus 1 like that. That way we're balancing it out and everything. And then what we're going to have is that factors as x plus 1, and then plus 9 like that. So that can be written as x plus 1 to the second plus 9. You can do all that in your head if you want to, okay? So what we're going to do is we're going to go ahead and just rewrite this integral like this. We have dx, and then just replace the denominator with x plus 1 to the second, and then plus, I'll write that as 3 to the second, because in this formula, a is what you're squaring, like that, okay? So that shouldn't be anything new to you. Everybody with me on that? Okay. All right. Now, we're going to do a U-substitution on this, just kind of a real simple U-substitution. So we're going to let u be this. So u is going to be x plus 1. Okay, and then that leaves us with du being dx. Okay, so then we should have a nice integral to do. So a lot of times before you go to the integral table, you want to use U-substitution and kind of get it all set up. Okay, so what we're going to have then is we're going to have dx becomes du. Okay, now the denominator becomes u squared plus 3 squared like that. Okay, so we've already learned this formula before too. This is a formula that's kind of nice to know because it does actually show up quite a bit. So what you're doing in here really is, this is u, a is 3. So we're just going to substitute in the values that we have, and then we'll have the answer to our integral then. So this is going to be 1 over, and I think I put the wrong thing there. A is 3, not u. So a is 3, and then x is u. So what you would have is you would have 1 over 3, and then you would have inverse tangent, u over 3 plus c, and then the last thing you got to remember to do is plug back in the u like that. So that would give us 1/3 inverse tangent x plus 1 over 3 plus c should be the answer to that problem. Okay, that really shouldn't be anything new to you. I'm just showing you that you can get that, look that up in the integral table as you need to. Okay. All right, is there any question on that? Does that look okay to everybody? Okay, how do you know to complete the square? Well, it's a quadratic, and the integral table, that matches that structure x squared plus a squared, so you have to do the complete the square to get that set up like that. Okay, any question? Everybody okay with that? Okay, all right, let's look at the next one here. We probably haven't ever looked at this formula before, so this one has this structure, kind of. Now, if you look, it doesn't initially look like it has that structure, although it does have the square root. And then there's a, 4 would be like the a squared. That e to the 2x, we're going to try to transfer that into like a U-substitution integral like that. So let's take a look at doing this one just by U-substitution, okay? What do you think would be a good thing to set u equal to in this problem? E to the x, good. And then when you have du, so you'll have the rest of the integral anyway. So that thing right there, we're going to set that equal to e to the x, okay, like that. And then that means that du is going to be the same, e to the x dx. So this whole thing right here is going to get replaced with du like that. Okay? Now, the next thing you gotta write this out like this. See, if you have e to the 2x, that's really e to the x to the second, right? It's the same thing. Okay, so what we're going to do is I'm going to write this then like this. My u substitution, I've got du is what I'm going to replace e to the x dx with. Okay, then in the denominator I'm going to have u is going to be e to the x, so that's going to be u squared. And then I'll write that I'll just leave that alone like that, write that like that. Okay? Does that make sense to everybody, what I'm doing? Okay? The key thing on that sometimes students don't see is e to the 2x is e to the x to the second. Then that just becomes u to the second when you replace that value with u like that. Okay, now what we're ready to do is we're ready to go straight to the integral table now. So basically what we have is everywhere you see x in this formula, that's going to be the u part. And then the a squared is going to be the 4. And then we just plug in and then we're pretty much done. We just substitute back in u like this. So what we're going to have for our answer is we'll have natural logarithm of u plus square root 4 plus u squared plus c, and then what we need to do is just substitute back in for u. U is e to the 2x, so we're going to plug that, or I'm sorry, e to the x is what u is. So we just plug that back in like that, and we should have an answer to the problem. Okay, so let's see what we got. We have ln e to the x, then I've got 4 plus e to the x squared, plus c, and then you want to just write that e to the x squared as e to the 2x. Remember, you're multiplying the exponents, so the best final answer would be ln e to the x plus square root of 4 plus e to the 2x plus c like that. Okay, and that should be the answer to the problem. Okay, all right, so one of the things that you have to do when you're doing integrals with an integral table is a lot of times you have to do u substitution, kind of get them set up. The big thing I would see on this one is it's got a square root and the structure is something squared plus a squared. Okay, does that make sense to everybody? Okay, now the way I test over this generally is I give you a very small table. I mean, it may have 5 or 6 integrals on it, and then you just match it up. I just give a couple of these on a test. These last two I did are pretty good examples. You have to do a little u substitution and then match it up with the right integral formula. Okay?
Would that fall out of the square root, the answer?
No. Okay? If you're thinking this, you might possibly be thinking this. Are you just looking at this part right here?
Yeah.
Yeah, okay. Now that doesn't come out of the integral. A lot of times students think this happens. The reason that doesn't happen is because of the plus sign. So anytime you have, a good way to look at this and review this is like if you had the square root of 9 plus 16. You know that that's the square root of 25, so you know the answer is 5, right? It does not work to just break it up like that because of the plus sign. That's what keeps you from doing that. See, that would be 3 plus 4, so that would be 7. It's supposed to be 5. You see what I mean? Okay. What I think a lot of times students get confused on with this, and the reason that mistake's made, is because if you have something like this now, if you had 4 times e to the 2x, yes, it would come out of the radical then. Then you would have 2e to the x. Because the square root of even e to the 2x, that is taking the square root of something squared, right? So does that make sense? Be careful about stuff like that. Anytime you have a plus or minus separating terms under radical, you can't do anything with it. Okay, but you can if it's a time sign. Okay? Any other question with anybody on that? Okay? All right, now let's see. What next thing I want to do is just a couple more things. I want to look at an arc length, just kind of review a couple of applications on this, because a lot of times you may be doing an application and you may end up with an integral where you might not know an integral technique for it, so then that's when you look up integral tables. Okay, those you're going into engineering and science, you do integral tables a lot, actually. I mean, you just start looking things up, unless they're basic integrals that you remember the strategy on. So what we're going to do on this one is we're going to take this curve, x squared over 4, that's a quadratic. We're going to find the length of the curve on the integral 0 to 8. So the first thing is, the formula that we learned on that goes integral a to b, and that's the one that goes the square root of 1 plus f prime of x squared. So you've learned how to do that arc length formula. So we're going to, first of all, get everything set up, and then we're going to see what kind of integral we have then, okay? So the first thing I'm going to do with this is I have y, I'm going to write that as 1/4 x squared. Since you have to do a derivative in your arc length formula, you want to go ahead and do that first derivative. Okay, so that's going to be 1/4, and then the derivative of x squared, of course, is 2x. So you would end up getting just x over 2, or 1/2 x if you do that then. Okay, so I'll just write that as 1/2 x. Okay, so that's going to get plugged in right there, and we're going to go ahead and see what kind of integral we have then. So for our arc length, we're going to integrate from 0 to 8. Okay, we got a continuous function here, 0 to 8, and we're going to do the square root of 1 plus, and then replace the f prime of x with 1/2 x squared dx like that. So we're going to work out that integral, see what we get. Okay, all right, so let's see. This one we'd have integral 0 to 8. You're going to have 1 plus 1/4 x to the second. If you take a half x times a half x, you get 1/4 x squared. Then we have dx like that. Okay, everybody okay so far with everything? Okay, now we've learned how to do this type of integral before. We're going to now look at this integral formula this time. So what I see on this one is I've got a square root around the sum of two squares. So this one kind of has that structure, doesn't it? Okay, I mean, it has kind of a nice similar structure. You could go ahead and actually go directly to your integral table now if you want to. What I'm going to do is I'm going to work with this thing right here. I'm going to get like a common denominator, simplify it a little bit before I go to the integral table then. So let's write this as, let's just getting a common denominator. I'm going to say 4 over 4 for the 1. Then I'm going to write that as x squared over 4, like that. Okay, now that's going to give integral 0 to 8. Then I'll have the integral of 4 plus x squared over 4 times dx. The reason I'm doing that is because now that square root of 4 is a 2, so that will come out of that radical then. So I'll have integral 0 to 8, 4 plus x squared all over 2 times dx like that. And see, that matches this perfectly now. You have a square root of a squared plus x squared. So we're just going to apply the integral formula this time instead of doing any U-substitution or any techniques that we learned. So I'm going to go ahead and take the half out. See, that's a 1/2. So you're going to have 1/2 times the integral 0 to 8. And I'll write that as 4 plus x squared dx. Okay? All right, any question about that? Okay, so let's see. Let's look at your integral formula now. Now, basically in this, everywhere you see an a squared is going to be 4, and then everything else is just an x. We're not even doing a U-substitution in this problem. So all you should have to do is take this integral formula right here, and everywhere you see an x, leave that alone, and then everywhere you see an a squared, then you want to use a 4 like that. So what you'd have is x over 2. Like that. Now we still got to evaluate this integral though, unfortunately. So we have x over 2, then a squared is the 4, then we have plus x squared. Okay, then we have a squared against 4, so that's 4 over 2. Then we have natural logarithm of x plus square root, we have a squared. So let's see, that's 4 plus x squared. And that whole thing is going to get it evaluated from 0 to 8 like that then. Okay, so I think I got everything on there. Now let's see, did I forget my half? Yeah, I think I forgot my half. So you got this half times this integral. So you got to be super duper careful about stuff like that. Okay, so I've got the half, and then I just did the integral formula like that. Okay, how's that look to everybody? Okay, everybody following okay? All right, now we're going to work this one out. This one's not too bad to work out. I'm going to go ahead and just take this out. We'll go ahead and just get this down to an exact answer. So now we got to evaluate this integral. So let's go ahead and just finish that up on this one. So let's see, we got a half, and let's see, then we're going to plug in the 8. Okay, so I'm going to start by plugging in the 8 for x. So I'll have 8 over 2. Square root of 4 plus 8 squared. Okay, now I'm going to cancel that. 4 over 2 is 2, so that's going to be 2L natural logarithm of 8 plus square root of 4 plus 8 to the second. Okay, like that. Okay, now I'm going to put a parenthesis around that because that's the evaluation of the 8. Okay, then I'll do the second part evaluating the 0, which will cancel some of the stuff out, I guess, a little bit. Okay, so now I'm going to go here. So I'm going to have 0 over 2, and then times the square root of 4 plus 0 squared. Okay, 4 over 2 is 2. Then I'll have 0 plus, whoops, I forgot my logarithm. Okay, so I'll have this, so I'll have natural, let's see, I have 4 over 2, 0 over 2. I got that okay. Now I'm going to go 2 there, then natural logarithm of 0 plus 4 plus 0 squared, like that. Okay, and that's the arithmetic we're going to work out then. Okay, and let's see kind of what we got going on there. I do see one thing it cancels. And there will be a lot of just kind of simple arithmetic that's going to go on this one then. Okay, so it looks like we have a half here. 8 over 2 is 4. Okay, that looks like 64 plus 4. So that looks like a 68. Then we have 2 natural logarithm of 8 plus, and that again I think is 64 plus 4 would be radical 68. Okay, so that'll take care of that. Now that whole thing goes to 0. Okay, 0 times that, and you would have minus 2 ln, and then that's going to be right here. If you look at this, whatever you can do in your head, you can do that. What's that? That looks like a 2, doesn't it? That's just square root of 4 is 2. Okay, so that kind of helps that a little bit, so that gives that. And then from here, we'll just kind of see if we got like terms and just kind of put stuff together here. So it looks like what we have is, I'm going to go ahead and distribute the half through here. So I have a half times 4 radical 68 plus a half times 2 ln 8 plus radical 68, and then half times that 2 would be half times 2 ln 2, and then from there I think what we're going to have is that would be 2 radical 68 there. Okay, that's going to cancel the 2's out there, so that's going to be ln of 8 plus root 68, and then there that's going to cancel, leaving you ln 2 like that. Okay, now I think the only other thing I did on this, I think, is you can break up the 68 if you want to. So 68, I think that divides by 4. So if I do that, I think you have a perfect square factor. Is that 17? I think is what that is. Yeah, it's 17. Okay, so then what I'll do is I'll just write this as 2 times 4 root 17 plus ln of 8. Same thing here, I'll do that as root 4 17 minus ln 2 like that. And let's see, that would be 2 times 2 would be 4 root 17. And this would be ln of 8 plus 2 root 17. And then minus ln 2. Now that's as far as I'm going to take that. That's an exact answer. So that's a little bit of a pain to have to work out definite integrals. That's not too bad. That's got some basic arithmetic in it, so that would be the precise answer to the problem. That's the exact length of that curve from 0 to 8. Okay? All right, so what you're trying to do in here, 3 basic things is doing the arc length formula that we learned. and using the integral table and then the evaluation of that integral. Okay, does that look okay? Okay. A little messy, okay, just a little bit messy on the arithmetic there, but not too bad. Okay, any questions about anything? Okay, so integral tables are real important things to learn how to do. I'm going to do one more, which I think is going to show you a reduction formula. One thing I wanted to point your attention to, I want to go back a little bit before in the notes, because these reduction formulas actually come in real handy. So these things right here, we've learned how to do powers. Like in a previous section, we learned how to do powers of sines and cosines, and some other ones too. But you can also use reduction formulas too. So if you're using powers of trig functions, most of the time what you do is you do reduction formulas. Okay, so I'm going to show you, I think, the tangent one. And these things are pretty powerful formulas when you're dealing with powers of trig functions. So let's do one of these to kind of finish this section up then. Okay, so tangent of the fourth power. So let's just work out this one. This is the reduction formula for the tangent. You might write a note of that because these are kind of important formulas to be able to look up. I don't expect you to memorize the reduction formulas, but they're not that hard to memorize. So the idea with this is this one we're going to have to do a U-substitution on, because the reduction formula is just looking at tangent to some integer power of x. Okay, so we're looking at some whole number power, like first power, second power, and so forth like that. Okay, and n cannot be 1, so you're generally looking at whole numbers starting with 2, okay? Whole number powers of a tangent. Okay, so let's let u be 3y, okay, and then du is going to be 3 times du, okay, like that. And then I'm going to divide both sides by 3 to get 1/3 du. Whoops, that's not what I wanted to do. That should be dy. Okay, like that. Okay, now let's see. Divide by 3, so we'll have 1/3 du is equal to 3 times dy. Okay, like that. Okay? Except I don't want the 3 there. I'm trying to show a step in my head and I'm screwing up. So divide by 3 like that. Now we've got 1/3 du is equal to dy. Okay, so now we're ready to kind of get everything set up. Then I'll show you how to use the reduction formula. So what we'll have for our u integral is we're going to have tangent 4. The 3y is going to become the u. Okay, so I'm going to write that as tangent to the fourth power of u. And then the dy is going to become 1/3 times du. Okay, so that's how that is going to get set up for our integral then. Okay, so now when we do this, actually it's pretty simple when you do this reduction formula. First thing you do is you do this piece right here. And that's just going to be tangent. Now I'm going to have the 1/3. And I'm going to draw kind of a big bracket right here. So the first thing I'm going to do is I'm going to do this, which is real simple. You just take that power and make it go down 1. When it says n minus 1, that's what's that's saying. So what's that going to be? That's going to be tangent to the third x over 3, like that. That's what that piece right there. We call it a reduction formula because the powers go down. And eventually we get down to a power that we might know how to do then. Okay, now the next part of this is we have an integral. So we're going to have the integral. Now the power goes down 2 when it says n minus 2. That 4 goes to a 2. So we'd have tangent squared x dx like that. And that would be step 1 of the reduction formula. So it's real simple. It's just, and it's not that hard to remember. First thing goes down 1 power, and then the integral goes down 2 powers, like that. Okay? Now, the tangent squared. The thing on this is that you can do with the reduction formula, this part right here, you can just use the reduction formula again. Okay, so that's what I'm going to do. Instead of going to the side and trying to think about how I would work out tangent squared, I can just use the reduction formula again. So watch carefully how I do this. Okay, so I'm going to have 1/3, and then I'm still going to have this piece, so I'm just going to write that as 1/3 tangent cubed x like that. Okay, now I'm going to have, I'm going to put like a new parenthesis here, kind of like that, because then I'm just going to start the reduction formula over again like that. Okay, so reduction formula goes like this. All right, look at the first part right here. So what's that going to become? Now remember, we're reducing the tangent squared, so what's that going to become? Tangent to the first, right, over 1. Okay, so I'll just write that as tangent to the first x over 1. That's what that piece is. Now what's the integral going to be?
1.
Tangent, yeah, it'll be 1 because it'll be tangent of 0, right? Because it goes down 2. So that's going 2 minus 2, so that'll be the integral of the tangent 0 dx like that. Yeah, and anything to the 0 power is 1, so you got a super easy integral. You just integrate 1. So see what I've done is I've done that reduction formula twice. Everybody see what I'm doing okay? All right, so you can get those reduction formulas all the way down to that 0 power, and it makes it pretty simple by doing that more than once. Okay, so now what we have is we have 1/3, then we have 1/3 of the tangent to the third x, minus, now I'm going to distribute that minus, so I'm going to have just minus tangent x there, minus a minus is a plus, so that's the integral of 1 times dx like that. Okay, now it's pretty simple to finish up. I'm going to have 1/3 times 1/3 tangent cubed of x minus tangent of x, and then the integral of 1 is x, so I have that plus c. And now these are, you know what, I'm kind of being a little sloppy on here. I don't know if you guys noticed or not, but you know what these things should be? I'm kind of being sloppy, and I'm just looking at the formula, so I need to correct this. That's really bad, and this is all in terms of u, so let's get all that fixed. I'm not paying attention, because we also got to do that evaluation. So we're going to have like tangent cubed u, tangent squared u du. So I'm going to go back and just kind of fix all these variables. Okay, so now I'm good. All right. So now what I want to do, I'm going to multiply it out, then I'll just substitute in my u. So I'm going to do like 1/3 times 1/3 is 1/9 times tangent cubed of u, and then I'll have minus 1/3 tangent u, and then I'll have plus 1/3 times u plus c. Then I can plug everything back in. So what, if you look at the u substitution I did, is just everywhere I see now a u, I just put in a 3y, then I should have an answer. Okay, so you got to have the u variable, then you got to substitute back in, so be kind of cautious about that. So it looks like that'll be 1/9 tangent third of 3y minus 1/3 tangent of 3y, and then the last thing is going to be 1/3 times 3y. That will cancel out the 3, so there's your answer right there. Okay, so that's pretty slick. The reduction formulas are very nice formulas to know, and what they work for is your integral table will have a reduction formula for each of the trig functions whenever you have powers of trig functions. Okay, like that. We kind of focused mostly on doing sines and cosines up to about the 4th power. Once it gets beyond that, it's pretty nice to just be able to apply a reduction formula. Okay? Okay, did you guys follow what I did on that okay? Okay? All right, and the key thing on that is don't forget, you can use that twice. If you want to, what you generally want to do is get that last integral down to a 0 power. And then it's a piece of cake. So we didn't have to integrate anything except the integral of 1 du. That's about as easy as it gets, right? Okay, so that's it. The other thing that this section talks about, and we don't really do that in Calc 2, but as you go into higher studies, you'll start seeing some of these computer software programs a lot. Maple is a real common one. You might begin to see that a little bit in Calc 3 or Diff-EQ. What they do is, and even like the TI-89, okay, it'll integrate stuff for you algebraically. So, I mean, you can just put stuff in there and it'll do the algebra for you. So, in the modern world, you know, of engineering and science and so forth, a lot of integration is going to be done for you. But, you know, you're at the stage where you're learning the concepts behind integration. So that's why we're going through all the details of that. But you'll get away from doing lots of integration by hand, which isn't a bad thing. What do you think? Yeah, okay. Actually, of course, in engineering, the hard part is setting up the mathematical model. That's the tough part. And then you kind of, in the modern world, you let computers take over quite a bit. So you'll probably see Maple and probably Mathematica are two nice systems that you might learn something about. Okay?